Hi, in this lesson, I'm going to discuss two different questions from two different years. Both questions are related to error calculation. First question from January 2021 IAL paper, question number 4, right? Fourth question, January 2021. So that question says a cylindrical container is made from a transparent material. Two students want to determine density of this material. The students need to make measurements to determine the volume of the transparent material. The external diameter of the container is approximately 10 centimeter. So student A suggests measuring the external diameter with a ruler. Maybe he would have an idea. Measuring the diameter means he would have kept a cylinder like this on a white sheet, and you can use two set squares like this. You can keep two set squares like this, and you can mark the positions, this position and this position. Measure this length by using a meter rule. That will directly give the diameter. So student A is suggesting this method to record the diameter by using a meter rule. Student B is suggesting he wants to use a string and wind it around the cylinder. So that will be the circumference. So the length of the cylinder which is wound on the cylinder will be circumference, that will be C equal to pi r or pi d. He wants to measure that length of the string, that is the circumference, by using a meter rule. Then he will divide it by pi, he will get the diameter. So anyway, both strands are measuring the diameter by using the same instrument, meter rule, but different approach they are doing. First one is directly measuring the diameter by using a meter rule. Second one is measuring the length of the string which wound on the circumference. So that means he is measuring the total length of pi d. From that he is going to calculate the d. The measurement both are done by using meter rule. The question is, explain which of these measurements would have the least percentage uncertainty for diameter. Okay, so there, when you think about the first measurement done, the measurement done by the student A, he is directly measuring the diameter. So for him, percentage uncertainty, so I can say for student A, so that is question number 4A part, percentage uncertainty will be the uncertainty, because he is using meter rule, so uncertainty will be 0.5 millimeter divided by the diameter he measured d. I don't want to substitute. I can substitute. They are saying almost 10 centimeter, but I am not substituting it. Just put d into 100%. For student B, he is measuring the circumference by using a string, and finally that measurement is done or taken by using a meter rule. So for his measurement, that is circumference, he is measuring the circumference. So percentage uncertainty in C is equal to the uncertainty in the measurement is 0.5 millimeter, because he is also using the meter rule. 0.5 millimeter divided by, I can remove the unit, 0.5 divided by the pi d, that is the circumference. C is pi d into 100. So you know that the numerator is the same in both methods. Here this is d, this is pi d. You know that pi d is greater than d because pi is a number 3.14. So for student B, the percentage uncertainty in C will be smaller than percentage uncertainty calculated by student A. So percentage uncertainty of C is smaller means, I told that now he is going to calculate the D by dividing the measurement by using pi. So percentage uncertainty in C is same as percentage uncertainty in D, because I told that whenever a measured quantity is multiplied or divided by a number, percentage uncertainty will not change. Percentage uncertainty will remain the same. So he is measuring pi d. The percentage uncertainty in pi d is equal to this much, which is smaller than percentage uncertainty of this one, because the denominator value pi d is larger than d. But we know that finally he is going to calculate the d by dividing the value of c by pi, but when you is dividing the value of c by a pi, the percentage uncertainty will not change. Therefore, percentage uncertainty in c is same as percentage uncertainty in d. So I can say percentage uncertainty in d is same as percentage uncertainty in pi d. So student B will get smaller value. So the student B will get the lowest percentage answer because his measurement is larger. So you should write both students have the same uncertainty 0.5 millimeter. Student B is taking larger measurement which is pi d. Therefore, percentage uncertainty of pi d will be lower than percentage uncertainty of d measured by student A. Therefore, student B will get smaller percentage uncertainty. Okay, so B part, question number 4, January 2021, Unit 6 paper. The students decide to use string to determine the circumference of the container. They measure the thickness T of the string using micrometer screw gauge. Explain two techniques that could be used to measure make sure this measurement T is as accurate as possible. So first, they are going to use micrometer screw gauge. First important thing, check for zero error to eliminate systematic error. Check for zero error of the micrometer screw gauge to eliminate systematic error. Measure the thickness at different points and find the average value to reduce the random error. So whenever you say random error, you should use the word reduce to reduce the random error. So again, I'm telling, check for zero error to eliminate the systematic error. Then you can say measure the thickness at different points of the cylinder and find the mean value to reduce the random error. Okay, B part, second part, following measurements to obtain for the thickness in millimeter, 5 different readings are given. So that is question number 4, part B, second part. Calculate the mean value of T. T is the thickness in millimeter and its uncertainty. So you can say this is question number 4, part B, second part. Mean, mean thickness is equal to, you add all the thicknesses, 2.15 plus 2.06 plus 2.13 plus 2.08 plus 2.10 divided by 5. So you will get 2.10 millimeter. So uncertainty in thickness, half into maximum value, that is 2.15, it's a repeated measurement, 2.15 minus minimum 2.06. So that will be 0.05 millimeter plus or minus. Okay, C part, first part. C part is given circumference. C of the container can be determined using the formula. So C is given. It's given by C is equal to x minus pi t, where x is the length of the string around the container. Calculate a value for C in centimeter. So the value of x is given 25.8 centimeter plus or minus 0.2 with the uncertainty. So C is equal to, so C part, first part, C is equal to, substitute 25.8 minus pi into, that is x is t is, we found it in centimeter, so 0.210 centimeter solid, you will get 25.1 centimeters. Now C part, second part, part C, second part, this part C, first part C, second part, show that the uncertainty is approximately 0.2. Careful here. So C is equal to x minus pi t means uncertainty in C is equal to uncertainty in x plus uncertainty in pi t. Uncertainty in pi t is equal to uncertainty in t into pi. You have to multiply this uncertainty by pi. That will be the uncertainty in pi t. So we'll find the uncertainty in pi t first. In pi t, you must multiply this by pi. I already told that in my error calculation lesson. So the link is given in the description part. You can see that. So pi into uncertainty is 0.05. So that will be 0.16 millimeters. So uncertainty C equal uncertain x plus uncertain pi t. I told that whenever two physical quantities are added or subtracted, uncertainties will be added. So uncertain x plus uncertain pi t. Uncertain x is given 0.2 centimeter plus, this is in millimeter. So to convert to centimeter, divide by 10. So that will be 0.016 centimeter. So that will be 0.216 centimeter. So approximately 0.22 centimeter. I can approximate. So approximately 0.2 centimeter. If I give it in 1 decimal point. Careful here. This must be multiplied by pi. Common mistake. You have to do multiplication there. Okay, so here how to find, I need to find the uncertain V. So to find the uncertain V, I should find the uncertain this one. This uncertain we already know that. So to find the uncertain this quantity, I should find the percentage uncertainty of this one, because this value, the Vi, is subtracted from this one, means uncertainty in V is equal to uncertain C squared L over 4 pi plus uncertain Vi. Uncertain Vi, we know that already. That is given in the question paper. So I need to find the uncertainty of C squared L over 4 pi. To find the uncertainty C squared L over 4 pi, first I should find the percentage uncertainty. If I know the percentage uncertainty of C squared L over 4 pi, if I find it, I already know the volume of it, so I can find the uncertainty of this quantity. Okay, so that's the first method. There's another method, we can do that. So in first method, I'm going to find the percentage uncertainty of this one. So percentage uncertainty in C squared L over 4 pi equal percentage uncertainty in C squared plus percentage uncertainty in L, because C squared and L are multiplied. 4 pi has no uncertainty because it's a number. So percentage uncertainty in C squared, you know the index come from 2 times percentage uncertainty in C plus percentage uncertainty in L. 2 times percentage uncertainty in C equal uncertainty in C, that we found it already in question part C, second part, we found it 0.22. So 0.22 over value of C, that also we already found it in question number part C, first part, 25.1 into 100. Percentage uncertainty in L equal, uncertainty in L is given in the question paper, that is given as 0.05 over 19.90, that also given into 100, you will get 2%. So uncertainty C squared L over 4 pi, the value of C squared L over 4 pi is 998 cm cube into percentage uncertainty, you will get the uncertainty, right? So uncertainty in V means uncertainty in this one plus uncertainty 5 cm cube, 25 centimeter cube. Okay, so second method to find the uncertainty volume, we found it already, that is 188 cm cube. That is only one method. Just substitute in this equation. Finding the uncertainty only, there are two methods. Already I discussed the first method. Now second method, find the V max and V min. So V max is equal to, I need to find the maximum value, that is C max squared L max maximum over 4 pi minus Vi minimum. I need to subtract the smallest value. So C max, how can I find the C max? You know the value of C is given. We already found the value of C in the previous part, 25.1 centimeter plus or minus 0.22 centimeter. So to get the maximum C, I should add the uncertainty. So 25.1. So 25.1 plus 0.22 all things squared. L max, L is given 119.90 plus or minus 0.05 given on the paper. So that is 19.90 plus, I should add the uncertainty, plus 0.05 over 4 pi minus Vi minimum. So Vi is given 810 plus or minus 5. So I should separate the smallest value of Vi. So that is 810 minus 5. So that will be the smallest value of Vi. So solve this one. You will get the maximum value, that will be 212.80 cm cube. Same way find the V minimum. That will be C minimum squared into L minimum over 4 pi minus Vi maximum. I should subtract the largest value of Vi. Then only I'll get the minimum value of Vi, minimum value of V. So C minimum, that will be 25.1 minus 0.22 all things squared into 19.90 minus 0.05 divided by 4 pi minus, this one will be 810 plus 5. So this answer, V minimum, you will get it 162.80. So I'll write it here, 162.80 cm cube. Okay, so I know the minimum value of V and maximum value of V. I need to find the uncertainty in V. So I can say uncertainty in V equal half times V max minus V min. Already I told that in my lesson. The link is given on the in the description part. So half into V max, that is 212.80. V minimum 162.80. Solve it. You'll get the same answer what we got in the first method. Here also you'll get the same answer. That will be 25 cm cube. So whatever the method we follow, the final answer will be the same. Okay, so part E of question number 4. The table shows the densities of some common material used to manufacture this type of container. Only borosilicate is safe to heat directly with Bunsen burner. So they are giving 3 different materials and their densities. The mass of the container, the mass what we used the laboratory, is 463. The mass is given as 463 gram plus or minus 1 gram. That's answer, Tim. Deduce whether the container is safe to heat directly with Bunsen burner. So here also I can do 2 different methods. I already found the volume of the container in the previous part, that I got 188 cm cube. I'll know the mass, so I'll find the density. Then I should find the uncertainty in density. Then find the range of the density in my experiment, right? Then check whether this value is falling within. So one by one we will check it. So only borosilicate is safe to use. So only the borosilicate should fall in the range of my density, the experimental value. Then I can say it could be a borosilicate, right? We'll try that way. So first we'll find the uh, density of the container we used in the laboratory. You know, density equal to mass over volume. Mass is given 463 gram divided by volume. We found it 188 centimeter cube. So that is 2.47 gram per cm cube. That is the density of the container I used in the laboratory. Okay, so this is not equal to any of these values. So I need to find the range of the density what I use in the laboratory. So I'll find the uncertainty. To find the uncertainty, I should find the percentage uncertainty first. So I can say percentage uncertainty in rho is equal to percentage uncertainty in mass plus percentage uncertainty in volume. Percentage is uncertainty in mass. Uncertainty in mass over mass. So 1 gram divided by 463 grams into 100%. Percentage uncertainty in volume. Uncertainty in volume, I found it already previous part, 25 cm cube divided by the volume of it, 188 into 100%. So that will be 13.5 percentage. I should find the uncertainty in rho. So I know the density 2.5, 2.4 gram per cm cube into 13.5 over 100. So that is going to be plus or minus 0.33 gram per cm cube. So range of my density, that is 2.4 gram per cm cube plus or minus 0.33 gram per cm cube. So my experimental value, the range of my density will fall from 2.14 gram per cm cube to 2.80 gram per cm cube. Now check for one by one. Now this density, soda glass, is also falling within this range. Borosilicate is also falling this range, but not this one. So I can say only thing like this: the density of both soda glass and borosilicate is falling within the range of my experimental value. The material I use in the laboratory could be either soda glass or borosilicate. So it is not safe to use Bunsen burner, because Bunsen burner can be used only for borosilicate, not for soda glass. So I should give that conclusion. So this is the method one what I used. Okay, second method. I'm going to find the percentage uncertainty same as the method one. Okay, so I already found it in the previous part. I'm keeping it on the board. So this is the density I found it. I need to find the percentage uncertainty. So percentage uncertainty, I need to find it again. Percentage uncertainty in rho equal percentage uncertainty uh, in mass plus percentage uncertainty in volume. So I erased it, I'm doing it again. That is percentage uncertainty in mass is 1 over 463 into 100% plus 25 is the answer in B. 25 over 188 into 100. So that will be 13.5%. Now, I am not going to find the range. I need to find the percentage difference between my density and each of them one by one. So I can say for soda glass, percentage difference equal. So that is 2.52. This is 2.4. So 2.52 minus 2.4 over. This should be taken as actual value 2.52 into 100%. Find the percentage difference. Okay, so 2.52 minus 2.47 over 2.5 is 2.47. If you give it in 3SF, yeah. So that will be final answer. This percentage difference will be 2%. So that is less than, I can say 2.0 percentage. So that is less than percentage uncertainty, that is 13.5. So it could be soda glass. So I told that earlier also. If you want to accept a value, the percentage difference should be smaller than percentage uncertainty. So here percentage difference smaller than percentage uncertainty for soda glass. For borosilicate, percentage difference is equal to difference, that is 2.47 minus 2.23 over 2.23 into 100%. So that will be, normally give it in two significant figures for 11 percentage. That also less than percentage uncertainty. So that means I can say it could be borosilicate. Okay, so we'll test for the last one, perspex now. So there also you can find the same way. That is for perspex. Percentage difference will be difference over 2.47. That's the laboratory value we got it, minus 1.18 over actual value we take it as 1.18 into 100%. That will be a big value, 109%, or we can say 110% to SF. So which is greater than percentage uncertainty. So cannot be perspex. So two different materials are agreeing. So final conclusion you should say same as what I wrote here earlier, method 1. Here you can say since the material used in the laboratory could be either soda glass or borosilicate, but only borosilicate could be used in Bunsen burner. So this material cannot be used in Bunsen burner because they are saying only borosilicate can be used. But here, according to this experiment, we are not sure whether it is borosilicate or soda glass because both are satisfying our condition. So the conclusion we should say it could be either borosilicate or soda glass. Therefore, it cannot be used in Bunsen burner. Okay, so I hope you understood this example. This is slightly different type of error calculation because you know the equation which is given as V equals C squared L over 4 pi minus VI. Some students get confused. Anyway, but I hope you understood this method, the both methods I did in the earlier part. Okay.